We're taught from a young age that our solar system is a neatly organized place. 8 planets moving reliably around the sun on a relatively flat, predictable plane. A formal vote in 2006 reclassified Pluto as a dwarf planet, effectively cleaning up the map and leaving us with a tidy 8-planet model. But if you travel billions of miles outward, past Neptune, that orderly system falls apart. You enter the Kuiper Belt, a massive ring of frozen debris where the normal rules of orbital physics don't seem to apply. Out here, we find a scattered population of distant, icy bodies known as extreme trans-Neptunian objects, and instead of tracing neat circles around the sun, they follow highly elongated, stretched-out paths. Those paths aren't level either. They are tilted at odd angles, dipping up to 30 degrees off the flat plane where the major planets live. This graphic maps out those bizarre orbits. Notice how, even though these icy bodies move at completely different speeds, their elliptical paths are overlapping and clustered, pointing in the exact same direction. The statistical probability of these distant space rocks aligning like this by pure chance is roughly 0.007%. The math dictates that a massive, unseen gravitational force is actively herding them together. In 2016, researchers at Caltech ran computer models to calculate exactly how much gravitational pull was required to create that specific orbital alignment. The data pointed directly to a hidden celestial body. They called it Planet 9, a theoretical super-Earth estimated to have a mass 5 to 10 times greater than our own planet. It would sit incredibly deep in space, up to 800 times further from the sun than we are. At that extreme distance, it would take up to 20,000 years to complete just one lap around the sun. Astronomers now have a highly detailed mathematical profile of a massive planet, including a strong estimate of its mass and its trajectory. Yet, when they look closely at the exact region of the sky it should occupy, they detect absolutely nothing. How exactly does a world up to 10 times heavier than Earth manage to stay entirely invisible? Traditionally, we locate planets by looking for visible sunlight reflecting off their atmospheres and bouncing back into our telescope lenses. But light dissipates over distance. For us to spot Planet 9, sunlight has to travel billions of miles out, hit the surface, and travel all the way back to Earth. Because of this two-way energy decay, a planet sitting 10 times further out than Neptune appears roughly 10,000 times fainter to our instruments. So rather than looking for a reflection in visible light, researchers decided to search for the planet's own internal heat using thermal radiation. By shifting to infrared observation, that thermal heat signature only has to make a one-way trip to Earth. This dramatically reduces the energy loss, making the hunt physically possible. To track down that heat, astronomers dug through decades-old databases from the IRAS and Akari sky surveys, searching for faint infrared dots that moved across the 23-year gap between the two missions. Tracking movement in deep space comes with a massive observational hurdle known as the parallax effect. Because Earth moves around the sun, our viewing angle shifts. This creates a false visual shift, making distant objects look like they're wiggling against background stars. To filter out this false wobble, researchers compare images taken on the exact same date across multiple years. By fixing Earth's position, they isolate the true, slow trajectory of objects moving independently. Comparing those two massive databases yielded 13 potential infrared matches that demonstrated actual, independent movement. After rigorous analysis, they narrowed the field down to a single, highly promising candidate that moved steadily across that 23-year observation gap. For the first time, researchers have a tangible target to point their telescopes at. A promising dot in archival data is an incredible lead, but it still requires confirmation through modern, active observation. We already know exactly where not to look. Sweeping sky maps generated by the Pan-STARRS telescope in Hawaii have systematically eliminated 78% of the planet's theoretical hiding spots. The remaining sections of the sky are currently waiting for the Vera C. Rubin Observatory. Expected to begin operations in late 2025, it features the world's largest digital camera, built specifically to rapidly scan the darkest patches of the southern hemisphere. With this level of next-generation hardware coming online to map the remaining search grid, humanity is positioned to definitively prove or disprove the existence of Planet 9 within the next 10 years. Confirming this discovery would officially add a massive super-Earth to our solar system. Planets of this size are the most common type of world we see orbiting other stars in our galaxy. Discovering one locally means we will have to completely rewrite our models of how our own planetary system formed. We routinely map the atmospheric makeup of alien planets residing thousands of light years away, yet we maintain a glaring blind spot right at the physical edge of our own cosmic neighborhood. The math tells us it's there, and the ongoing search is a humbling reminder that vast areas of our solar system remain entirely unexplored, leaving plenty of room in the dark to hide a giant.